The first will focus on routers and the second will focus on switches. And we're going to go through the step-by-step process of what needs to be done if you have a brand new router. I mean, what does need to be done? You need to do things like make sure an interface is up and active, set the things like the speed and duplex. We'll take a look at how those interact with the interface, and give it an IP address. For routing, we need to train the router, either with static routes or use a dynamic routing protocol. So one of the cool things is that we'll get to review some of the concepts that we learned in the IP addressing section and also in the routing section and apply it as we bring up a router. Let's jump in. I still remember when I first started working with computer networks and PCs in general back in the 80s and putting the networks in place. That was a lot of fun because when you're done, you can see, like, I put this in place, I built this, I made this work. It's like Tinker Toys, putting them all together. So in this nugget, we're going to focus on the routers, configuring them. So let's use our topology. We've been working with this topology so far. So we've got R1 right here, and I've got R2 right here. So these are physical representations of the routers, and these are the icons that we'll normally see in a topology. So you'll normally not see both, but the reason I've included it is so you can see every time when you see router, you'll think, okay, there's the hockey puck, there's the icon, and there's the physical device. For switch, there's the icon, and there's the physical device. So if we take a look at R1, it's got a couple of interfaces. It's got 1/0 and 1/1. And the way that most vendors deal with these interfaces, they might refer to them as Ethernet, like with an E for short, for Ethernet, which is the type of networking we're doing here. It's a layer 2 standard and has some physical guidelines as well for it. So somebody might call that E1/0. A different vendor might say, well, there's 3 different flavors of Ethernet. There's Ethernet, which is 10 million bits per second, called Ethernet. There's 100 megabits per second, and they call that fast Ethernet. So I'll put little letters there. And then there's 1,000 megabits per second, and they call that gigabit Ethernet. So if somebody says E1/0, 20 years ago, that would mean, oh yeah, it's 10 megabits no matter what. But now sometimes if they refer to it as E1/0, depending on the vendor, it's just some type of Ethernet. Maybe it's working at 10 megabits or 100 megabits or a gigabit. Cisco, when they do their interfaces, if this interface is capable of 100 megabits per second, they'll refer to it as fast Ethernet. And then it'll be a slot number and port number. So for example, this in a modular router, in fact, let me show you. Let me show you what a modular router looks like. So this is an example of a router from a vendor. It happens to be a Cisco router. This is the front side. It's a 3900 series. It's got a power supply here, and it's got an option for another power supply there. So if one fails, the other one can keep going if they're both plugged in. Also, for fault tolerance, it would also be a good idea if we did have redundant power supplies to make sure that this one was fed by power source A and this one was fed by power source B, because if we have both interfaces on the router, both the power supplies plugged into the same power source, and the power source fails, the router is going to fail as well. So we want to have fault tolerance across the board. So this is the front side right here, and this is the back side. If you notice, we have some built-in ports right here. And these built-in ports, usually the built-in ports are referred to as slot 0. So the first port on slot 0 would be port. If they were gigabit Ethernet, it would be gigabit 0 for slot 0, port 0. That's the first interface. And the next one might be gigabit 0/1 and so forth. If we added modules to these slots, we would go ahead and refer those interfaces. For example, if we put a 2-port serial interface here, it could go ahead and be, if this was, and I'm not sure on this model, but let's say this is slot 0, that's slot 1, and slot 2. If I was referring to the first interface on slot 2, it'd be serial, if it was a serial interface, 2, referring to the slot number, port number 0. So whenever you see two numbers with a slash, or some modules have, for example, maybe a 3/2/3, that'd be a slot and the actual module and then the actual port. So it just depends on the device, but that's just a heads up on the numbering that a lot of device vendors use, and they usually start with 0. So let's populate this. Let me show you an example of this modular router. And it's modular because it's got slots that you can add hardware to. So let's say we want to use this router to connect to Reno, Nevada from Las Vegas, from our headquarters site. How do we get there? Well, first of all, we purchase a circuit. We purchase some bandwidth and a circuit from a service provider, and then we would use we could use a serial interface to connect to it. So if we want to bring in a serial interface, we could just install one like that. And poof, now we have let me move it over here. There we go. That way it matches our analogy from before. Now we have a 2-port serial interface, and we can use serial connectivity to go ahead and connect up to the remote site. So that's how easy it is. Now a lot of these are not hot swappable on most vendors' gear, so you'd want to power off. So go to the front, power off the device, put the module in, power it back up. When the operating system boots up, it'll see the new hardware, and away you go. So if we want to take a few more modules, for example, let's take a T1. There we go. So there's 4 T1 ports right there. And T1 describes a couple of things. It describes some technology for signaling. It also describes capacity. We'll talk about that in another nugget. And let's see here. Do we have something big that we can put in these ones down here? Looking for a big port. Let me see if I can find one. Here we go. That's a slot cover. So you want it to be nice and pretty and to manage the airflow so the airflow goes through all right. So that's what a modular router is all about. You simply buy a router that has what you need, and if it's modular, you can add new modules in the future. Okay, so now that we've taken a look at this, what I'd like to take a look at is our network that we are playing with. Here's our network, and our goal here is to configure the router. Let me give you some heads up on the details here. So we've got router 1, it's got interface fast Ethernet 1/0 right here, and fast Ethernet 1/1. Remember that every network, every interface on a router is a separate street, a different IP subnetwork or network. So if we're going to have R1 participate on the 10.1.0 street, it needs to have an IP address. So what I'd like to do is I'd like to walk through these elements with you, you and I, and we'll configure it from the ground up. So let's begin with the first aspects. Here we have router 1, which is the same as this router right here at the command line interface. We'll be configuring him in a moment. And we're going to configure several aspects on each of the interfaces. So this is interface FA1/0. This is FA1/1. And we can configure the speed, the duplex, or we can simply say, go ahead and automatically negotiate that with the device you're connected to. So the router is connected to the switch, and if by default, they're going to automatically negotiate their speed and duplex. But let's take a look at why that might be important. If I have a fast Ethernet interface, FA for short, and this is 1/0, it could be operating at 100 megabits per second, or it could be operating at 10 megabits per second. And the biggest difference here is, what is it connected to? If it's connected to a device that only speaks 10 megabits right here at the switch for whatever reason, you'd want to make sure you set it for 10, or hopefully they would auto-negotiate that speed correctly. So you want to get that correctly set up. And the other option is duplex. We use like 99% of the time, we're going to use something called full duplex. And let me tell you what that's all about. Inside of our patch cable, from this PC to the switch, and from this switch to the router, in the patch cable, there's 8 wires. And we only really use 4 of them. So those 4 wires equals 2 pairs. Now, whether we're running half duplex or full duplex, we're going to use those 4 wires. In the world of half duplex, we are going to be connected, for example, to a hub. Now, remember how a hub works. It does no knowledge of layer 2. So when Bob here sends data into a hub, even if it's a unicast frame, layer 2 is destined for a specific printer or another resource, the hub is going to forward it out all of the other ports. So because the hub operates in this manner, we have to turn on something called collision detection, because it's one giant collision domain, meaning everybody has to share the road. So if Bob's sending traffic, everybody else has to do nothing but simply listen, and when Bob's done, somebody else can try to send. Half duplex is sending or receiving, but not doing both at the same time and having to share all the bandwidth. That's half duplex. Well, then what's full duplex? Well, full duplex is when you're connected to a switch it can use one pair for sending, one pair for receiving, and the switch, because of its wonderful nature, is going to keep all the traffic separate. So with full duplex, we turn off carrier sensing multiple access with collision detection because we don't care. We're not going to have any collisions. We're not listening for collisions. That means this printer, this PC, if it's all full duplex, when they want to send, you know what they do? They send. And then the switch buffers all that in the background and moves it around to make sure there's no collisions that are happening. So long story short, full duplex is the way to go. And speed, you want to go as fast as both sides can allow. And if it's a switch, you're going to be using full duplex. If you're attached to a hub, it has to be half duplex. The other thing we're going to do is configure an IP address on this interface. So this is the 10.1.0 street. So we need to give this router interface an IP address that starts with 10.1.0, his street name, plus unique IP address. I think we'll go ahead and choose 1 because it's my network. So I'll show you how to do all of those right now. So this is R1. We'll go into configuration mode. Now, config T is short for configure terminal. And that's the way you tell a Cisco router that you want to go ahead and go into what's called configuration mode. And the actual syntax, I'm going to actually be fairly quick on it here because it's not a focal point for your certification in Network Plus. The goal is to realize that you know what you need to do? On an interface, you need to make sure it's up, make sure it's running, make sure the speed and duplex are okay, and then specify the actual IP address so that it can communicate. So that's what we're going to focus on here. So to go into that interface FA1/0, we go interface, fast Ethernet, 1/0. What I'm doing is I'm typing out the first couple letters of the command, and then I'm hitting the tab key so you can see the full syntax on virtually all my commands. So now you'll notice the prompt changed. We're now in interface configuration mode, and I'm going to go ahead and do the first thing that you should do on every router interface you want to use on a Cisco box, and that is to bring it up. By default, the interface is disabled. It's shut down by default. So to bring it up, you have to use this trick that I trained my dog to do, and it's called stand up. Here's how I trained my Cisco dog to stand up. I said, "Dear dog, no sit down." And so the dog, when I say no sit, it stands up. And that's how you bring up an interface on a Cisco router. No shutdown is the command to bring up the interface. So I want to run no shutdown first of all to get the interface up and working. If I want to set the speed manually, I can, but there's my options. I can say speed 10, speed 100. You can always go lower than your capabilities of your interface, but you can't go faster. So because it's fast Ethernet interface, it can go at 100, it can go at 10, and I can also leave auto on. Auto means it auto work. It's a joke. Auto means it'll auto negotiate the speed with the device it's connected to. And then for duplex, we could specify auto, which is the default, or we can set it to full if we know we're connected to a switch, and set it to half if we know we're connected to a hub. It's very important that both sides get it correct. Otherwise, if one side thinks it's full duplex and the other side thinks it's half, one side is going to see a whole boatload of collisions, and the other side is not even checking for collisions. So it's important to get those correct. If you leave it to auto and you have intelligent network devices that are current and they're up to spec, they should work themselves out and correctly negotiate the best full and the best duplex and the highest speed possible. The last piece is an IP address. And the way you specify an IP address, and again, we're in this interface 1/0, is we say 10.1.0.1. That's the IP address I'm going to give it. Now, do you remember? Do you remember, my friend, from when we took the IP addressing nugget together? Do you remember how we can tell the router that the first 3 octets are the network and that the last octet is going to be left alone for host addressing? You remember the mechanism? If you do, that's awesome. It's the mask. It's always the mask that draws the line between network portion and host portion. So the 255 means that the first octet, or first 8 bits, are all network. This 255 means the second octet, the second 8 bits are all network. And the third octet of 255 means that the third octet is also all being used to identify the actual street or network. The last octet of last 8 bits, I'm putting a 0 in the mask, which means these last 8 bits, which are just a 1 in here in decimal, that complete octet is the actual host address. And press enter, and it's done. Now, how do we test that? We could do a ping. We could ping if we knew the IP address of this device right here. So let's configure interface 1.1 as well. We'll go to interface fast Ethernet 1/1, no shutdown, and we'll say duplex and speed. We're going to do that, have it negotiate it, and do IP address of 10.12.0.1. Now, how do we test that? Well, we could do a broadcast ping and see who responds, or we could just go up to a workstation and say, "Dear Mr. Workstation, what's your IP address?" This is the PC in the top left-hand corner right here. And we just say IP config, it's 10.1.0.53. We should be able to ping 10.1.0.53. Sure enough. Now, the very first time we tried to connect, my router didn't know the layer 2 address of the PC. So can you tell me what exactly did my router use to figure out the layer 2 address of the PC on that same subnetwork? What do we use to figure that out? Do you remember? If you're saying, Keith, it's ARP, you'd be absolutely right. And that's also why we lost this first ping packet. So the ping packet timed out. That's the symbol for timing out. We didn't get a response. But once we learned the layer 2 address, all the rest of the pings work. And now that it's in the ARP cache, the rest of the pings will work. We shouldn't have a failure again like that of that first ping because of ARP. Okay, awesome. So what's next in our list? Well, next we have routing protocols. Routing protocols. Keith, we had a nugget on that, right? Yes, we did. I was there. You were there. It was great. So what about routing protocols? What do we mean by routing? Well, routing can mean two basic things as a review. It could mean that we're either learning about networks or we're making forwarding decisions on layer 3 packets towards those networks. It's a very important two-step process. So my router right now knows about the 10.1.0 network and the 10.12 network, but he may or may not know about the rest of the world. So let's take a look. We'll go ask him. The way you ask a router on Cisco is you do a show IP route. And that's the command right there highlighted. And he says, nope, I just know about those two networks. Anything outside of those two networks, I don't know how to reach it. I'm going to drop packets. So in order to dynamically learn routes, we can just use a routing protocol. So which routing protocol should we use? Well, maybe the one that everybody else is using in your network. That's the right answer, by the way. If you want to run, like, for example, RIP or EIGRP, those distance vector or advanced distance vector routing protocols, you can if everybody else is running it. In this network, our other routers are running OSPF, so that's what I need to run as well. The syntax I'm not concerned that you memorize at this point because this is a Cisco router. If you take this and apply this all towards a Cisco Certified Network Associate later, you'll need to learn the commands specifically at that point. But for now, I'm simply going to enable OSPF on this router. I'm going to put a space there before the process ID. I'm going to say that all interfaces belong to OSPF, and they all are going to be in area 0. OSPF, again, is a link state routing protocol. So now that R1 is communicating and saying, hey, I'm willing to share, I want to be neighbors, basically R2 saying, hey, I'll be a neighbor with you. That's a neighborship message from OSPF saying, yep, I'll talk to you. And check this out. Look at our routing table now. We now have routes to all of our internal networks. This is up in Reno. That's our serial connection up to Reno. That's a connection off of Reno itself. There's our connection to the service provider of that network. We have the 10.2 network, which is where switch 2 is. We have 10.1, which we're directly connected to. And then we have this guy's up in Reno as well, off of R3. So we have a whole bunch of routes, but you know what we don't have? We don't have a route to the internet. And so I mean, out of all these routes we have, there's 400,000 routes on the internet. How do we reach all those? I want to add one additional special route that I don't think I spoke to in our basic routing section, but now it's appropriate time for it, and that is a default route. A default route is instructions to a router saying, dear Mr. Router 1, tell you what, if you get a packet for a network, you look at your routing table right here. and you see if you can make a decision on where to forward that packet to. But if you don't find a match in your routing table, you check everything, nothing's there, I want you to send it to this next hop. In this case, R1 would probably want to send it to R2. The way we do that is with something called a default route. I like to call it the Obi-Wan Kenobi route from Star Wars. Like Princess Leia says, "Help us, Obi-Wan, you're our only hope." And a default route is like that. A default route says, you don't know what to do, send it to me. So we'll create that. The way you do it on a Cisco router is I'm going to create a static default route. It looks like this. It's kind of funny looking. But that's the instructions for a default route. 4 zeros, a space, 4 more zeros. And then we say, who do you want to hand it to? So that default route says, if you don't know what to do, send it to 10.12.02. And if we look at the routing table again, there's our, it's also called a gateway of last resort. So PCs, when they're configured, they're given a default gateway. That's kind of like their default route, what to do if they don't know what to do with it. They hand it to R1. R1's default route is going to be R2. So gateway of last resort is to a Cisco router what a default gateway is to the PC. So default route. So now let's see if this PC can actually get to the internet, which would mean the PC would go down to R1, R1 would forward to R2, and hopefully R2 could forward it up to the internet. So we'll bring up the PC and we'll do a ping of google.com, and sure enough. And if this router right here wanted to ping that address of google.com, one of their servers, that should work also. But I'll tell you what won't work. Look at that. Why is that? Why can't my router get to google.com by name, but it can get there based on IP address? What is the missing factor? What is the magic that allows us to convert a name into an IP address? Because that's the problem we're experiencing right here with this ping to the name. And if you're thinking, Keith, it's DNS, UDP application, or it's an application layer program that uses UDP port 53 as its well-known port, I'd say, good job. And I simply haven't configured R1 to use a DNS server. That's why it's failing. Where the PC is using a DNS server, it can resolve the name, but we have connectivity because they both can reach that IP address by its IP address. So in this nugget, what we're going to do is I'm going to chop it up into 2 pieces. The first piece is going to involve the routers, and then we'll have part 2 of this, which will be the switches. But I'd like to take a look at the big picture with something called NAT and PAT, and then we'll also follow up with filtering and QoS. So let me clear off this for a moment, and let's look at the big network, and I've got a couple basic questions to ask. So here's my question and also kind of a problem. Inside, we learned earlier in IP addressing that we can use some RFC, which stands for Request for Comments. Those are the documents we use to communicate and share ideas and agree on standards. If we have RFC 1918 addresses, those are the IP addresses that are private. And here's how that works. And let's use an example. Anything that starts with 10 is an example of one of the IP addresses in this private range. So what we did in this company is we used the 10 network address space for almost all this. We had the 10 network that we used, and we cut it up into subnets as we discussed in the IP section. We have 10.1.0.0 here, /24. We have 10.2.0.0/24 here. Between these 2 routers, we have 10.12.0.0/24. So we have these subnets, and that's all well and good. But here's the problem. Service providers, they don't allow packets onto the internet if they're coming from a private address range, because some other company may also be using the 10, and another company may be using the 10 network, and they're all connected to the internet. So the internet service providers block and they filter everything that looks like it's coming from one of the private address spaces. So how in the world, Keith, did this computer, who has the IP address of 10.1.0.53, which was learned via DHCP, whose default gateway is here, .1, how did he get to google.com? I mean, we've been there several times. And you might be thinking, oh, Keith, well, it's simple. Here's how it works. This client, first of all, made a DNS request to a DNS server. Well, let's stop the truck right there. Let's say the DNS server is 8.8.8.8. That's also on the internet. How did the DNS request even work? Because the service provider is not allowing the 10 network out. The answer is we have to use something called lying. Now, normally lying is frowned upon and not a good idea, but lying is exactly what we're going to do, and we're going to do it on this router right here. Now, lying, another name for it is network address translation, or NAT. The lying part is just a little humor, but it's really what we're doing. And here's how the play-by-play goes. On this router, we've got a global address on this interface right here facing the internet. And maybe it's 24.0.0.2 or some other IP address that's globally routed on the internet. It's not a private address. It was assigned to us by the service provider via DHCP, or they told us to statically configure that IP address. Either way, it doesn't matter, but we have a global address here. And so what we could do is this. The need is for this, the printer really doesn't have to go out on the internet, but the need is for when these computers need to go out to the internet, what we can do is we can tell this router, R2, to go ahead and change out the 10.1.0. Let's say X addresses and replace it with a pool. So for example, let's say that the service provider gave us 24.0.0.5 through 20. So they gave us this pool of addresses, all globally routable. And every time a PC goes out to the internet, this router is going to say, oh, you're coming from 10.1.0.53. I will remember that, and I'll translate that over to 24.0.0.5. So the router's going to remember. It's like this game is playing of what lies it told, and then when the return packet comes in, it's going to untranslate that and traffic and forward it back. So in this router's table, it would say 10.1.0.53 is the inside host, but it's being translated over to 24.0.0.maybe 6 or whatever the IP address is. And so the internet would only see a packet coming from 24.0.0.6. When the reply packet comes back in, the router would see it and say, oh, that's really 10.0.0.53, and translate it back. That's called NAT, Network Address Translation. And that's the reason, by the way, that IP version 4 has been able to survive for so many years after we've run out of IP addresses. And that's still the case today. That's why it's still hanging around, is because we can hide the addresses behind NAT. Now, another problem is this. This company says to the service provider, can we buy a pool of valid global addresses? And they would say, yeah, it's thousands of dollars a month for a pool of addresses. And we could say, well, we don't have thousands of dollars a month that we can spend on that. Maybe we'll cheat a little bit. So the IP address of this interface is 24.0.0.2. We could use something called PAT, which is port address translation. And what it is, it's really a subset of NAT. It's like NAT's cousin. And here's how it works. Let's say I have these two PCs, they want to go out to the internet. Every time a PC goes out to the internet, what this router is going to do is going to say, okay, I'm going to translate the source address of 10.1.0. Let's say he's 53 and this guy is .54. I'm going to translate, when 53 goes out, I'm going to translate 53 over to my address of .2. But I'll keep track of the port numbers. See, this client's always going to use a source port, some random high-numbered source port, and it's going to track not only the IP addresses, but the ports involved. That's why they call it port address translation. So when this host .54 goes out, so let's say he was going from source port 3000. When host 54 goes out, it also gets translated to the layer 3 address of .2, but the ports being tracked maybe is 46,598, whatever port. And if two clients, for whatever reason, came and they both came on the same source port as they're making requests out to the internet, the PAT device could simply swap out one of the ports for a different one. And because it's tracking it all, it could restore it as it did the untranslate for the return. So that's what PAT is. NAT is swapping out a one-to-one IP address. This device gets one IP address on the internet. This device gets a different IP address as it goes out to the internet. That's NAT. When everybody's being mapped to the same IP address as they go out, it's considered overloading or port address translation, or PAT for short. So if somebody says we're doing NAT, it's very likely they're doing PAT because PAT indeed is a subset of NAT. So let's take a look at our next piece here in the routing section. That is the filtering of traffic. This user right here, let's say we want it to avoid having him send ping requests out to the internet. So no ping for you. So how do we enforce that? We could just ask him, say, could you please never ping? But you know what? As far as human nature goes and curiosity, that may not completely stop the problem, especially if there's a program in the background that's maliciously sending out ping requests or what have you. So how do we stop that? Well, the first thing we need to ask ourselves is, okay, ping. What protocol does that use? What does that use behind the scenes? And the answer is it uses ICMP. Now that we know it's ICMP, we could say, well, how do we filter it? What we're going to do is we could filter it right here on fast Ethernet 1/0 as that traffic tries to get into the router, or as it tries to leave the router. We could tell the router to watch out for it, pay attention to ICMP traffic, and if you see it, just go ahead and drop it. And that's how we could do it. And filtering traffic is as simple as creating a list of traffic that we'd like to permit or drop, and then apply it. So in our list, we could say no ICMP and allow everything else. I'll put everything else. And we'll create this list called an access list, also sometimes referred to as an access control list. And we'll apply it inbound on FA1/0. So let's do it as an example of basic filtering on a network. So we'll bring up our PC. And our PC's booting up. I just wanted to verify that beautiful Windows sound in the background. I just want to verify that we can ping first before we start to filter the ICMP traffic. So let's bring up a command prompt and ping to google.com. All right, that made it. And let's also bring up a browser just to make sure that ICMP from here is working and also HTTP still works. Make sure that somebody didn't turn off the internet on us. All right, and that's working too. Okay, so ICMP worked from here and our browser works. That's fantastic. Let's close that. We'll minimize our Windows machine. And then let's bring up the command line interface for router 1. So on router 1, we're simply going to create an access list. And again, the syntax at this point, I'm not too concerned with, but the function is what I want you to focus on. We're going to create an access list that says it's going to be 2 lines long. First line is going to say deny anything that looks like ICMP traffic. The second line is going to say permit everything else. So we'll go into configuration mode, and I'll say access list 100. Let's actually do something really important. Let's do a show access list. And just to make sure that we don't already have an access list 100, a lot of times people will create a new access list, or they think they're creating a new access list, but they're really just adding lines to the bottom of an existing one. So no access list in place. We'll create one. Access list, there's a couple of different ways we could do this. Let's do it this way. IP access list extended 100. So we're now in access list configuration mode. My first line, I'm going to say deny ICMP traffic from anywhere going to anywhere. And for my next line, I'm going to say permit IP traffic from anywhere to anywhere. So access lists are read after they're applied from top to bottom. So if we put this access list, assigned it to this FA1/0 interface, and it's like having a bodyguard at the interface. He's looking at every packet, comparing against the lines in the access list and saying yes or no based on the rule in the access list. So let's go apply it. We'll go to interface fast Ethernet 1/0, and we'll say IP access group 100. That's the list we just created in. So now it's applied. that access list is now watching all traffic as it's trying to come into the router on this interface. And if it's ICMP, it's going to deny it. If it's anything else, it's going to permit it. Let's go verify. We'll bring up our PC again. We'll go up to a command prompt, and we'll do a ping of www.google.com. And look at this. So you'll notice we have DNS is working. DNS is UDP, port 53, the well-known outbound port, destination port. So DNS is working for the name to IP, but the actual ping isn't working. And this response is coming back from 10101 saying, hey, buddy, you can't get there from here. And that's why the Windows XP machine is showing a message saying destination network unreachable. Let's see if we can get to open a browser. Hopefully we didn't just kill all traffic. So going to the same site, but now we're using HTTP, which is writing on top of TCP, which isn't ICMP. Now that makes it no problem whatsoever. All right, so that's an example of filtering traffic using a router and a layer 3 interface for filtering traffic inbound right there. The last piece I'd like to talk to you about in this part 1 of 2 of this section is quality of service. Now, everybody wants quality, right? I mean, I want to have quality in the service I give you, and if we go into a restaurant, we're going to want service from them. But quality of service as a response to networks is about treating people, or it's about unfair treatment. That's what QoS is. It's unfair treatment. But it's unfair treatment of packets on the network. And let me explain why. Let's say we're implementing voice over IP. So some of the protocols we talked about were SIP, the Session Initiation Protocol, and we also have RTP, that's the Real-Time Transport Protocol. This uses TCP for setting up the call. This is UDP for delivering the actual packets. So voice over IP, fantastic. So we have phone 1, and over here, off this switch, we have phone 2. And so we have a couple people. We have Bob over here and Lois over here. And they've initiated a phone call, and they're just talking at it and having a good time. The voice over IP is wonderful. It just works like a telephone, except all the data is being digitized as it goes across. So they're talking on the phone, and then all of a sudden, well, let's say about 35 people just get an email message, and it says, oh, go check out this video. And so these 35 people all send requests, 35 different machines. They all send a request to a web server right here, internally, pulling down a file. Maybe it's a video or something humorous, and they're all pulling down a lot of data. So this web server is sending tons of traffic this way to all these different users, and it's not multicast. It's like 35 different streams of unicast traffic just choking up the network. Well, at that moment, Bob and Lois start to have dropped. Is like a staticky call, like a really bad call that you're on, where you can't quite hear everything clearly. And Bob's saying, "Can you hear me, Lois?" And Lois is saying, "No. Well, what did you say? What did you say?" And it's all breaking up. It's breaking up. So, unfortunately, their application, the voice over IP that they were using so well a few moments ago, is now falling apart and not working well because of congestion on the network. There's just too many packets, and as the network tries to sort it all out, the voice call isn't getting enough to make it still successful. So what do we do to solve that? To solve that, we implement something called QoS, quality of service. Quality of service is being unfair to certain traffic when congestion occurs. For example, we could take the packets that come in from the phone 1, and mark them as, I'll use red, as S. Now S, for our discussion, means special. We could also take the traffic that comes in from phone 2 and mark those packets as special. We could mark everybody else's traffic as N. I'll put an N in blue here. So we'll say all the PCs are N for normal traffic. And we could also take some traffic called scavenger class traffic that we don't really care about at all, and we call it toss. Like toss this if you have to. It's not really important. It's like the bottom of the barrel. But the point of here is that if we mark all the traffic from the telephones as S for special, then what we can do as the congestion occurs on the network, we can tell this router, listen router, you've got 10,000 packets that need to be sent right now. Everybody wants you to send these 10,000 packets. what are you going to do? The router can say, well, you know what? I'm going to take all the special packets, send those first, and then I'll send the normal packets, and then I'll send the throwaway packets if they're still around. So basically, we're giving preferential treatment, QoS, quality of service, to certain types of traffic. Why? Because a telephone call, if it doesn't get the exact treatment, if it doesn't get there fast enough with enough consistency, the application, which is the voice call, won't be successful. If somebody's sending an email message to an email server, they're not going to notice if there's a few 100-millisecond delay, or even a 2 or 3 second full second delay, 2 or 3,000 milliseconds, because they hit send, the email goes. It's not a huge deal if it doesn't get there in the exact few milliseconds that they sent it. So that's what QoS is all about. So in this first half of our network installation and configuration, we've identified for interfaces that we need to bring an interface up, make sure it's accessible with the no shutdown command on a Cisco device. We want to make sure the speed is set correctly, and duplex for whatever we're talking with, half duplex for a hub environment, and full duplex for a switched environment. We also gave it an IP address appropriate for that interface. Routing protocols, making sure the router knows where the networks are. We could statically configure routes like we did with the default route, or we could use dynamic routing protocols to share information. And we could also inject a default route inside of a routing protocol. That's another option too. Because all these addresses here are using private address spaces, we need to use some kind of network address translation or port address translation to convert the source IP address of this PC out to a global address before it hits the internet. Why? Because the service providers will not allow source IP addresses in the private address space to be on the internet. Filtering is handy and can be done lots of places, including on router interfaces, by specifying what you want to allow or not allow. And then quality of service is to give preferential treatment by, first of all, marking packets as special, quote unquote, and then training the router to identify those special packets and give them preferential treatment on the network. And we'll take a look at the switching in part 2. So I hope this has been informative for you, and I'd like to thank you for viewing.